Yeah. Okay. Yeah. Yeah. I hope the screen is visible. Yeah. So if anyone wants to ask anything, feel free to interrupt me. Because don't type in chat section because I may not see it actually. Yeah. Yeah, so okay, so let's begin today's discussion. So it's on color coding and splitters. So it's quite a nice technique actually. Sort of like it's sort of a nice black box, these splitters, which can be used to properly brute force something. Like naive brute forcing is quite tough. Like some algorithms, if you try to do direct brute forcing, it might take a lot of time. But the splitters allow us to brute force in a very quick time actually. So we'll see it in the application point of view. But first, let's look at what splitters is. Okay. So before we start this thing, these are some standard notations which we follow. So this n this bracket denotes the set 1 to n, and then this notation, it represents set of all k-sized subset of this set. So take any subset which is of size k, and collection of all those subsets is represented by this. And z star p, we use it to denote this set 1 2 up to p minus 1.
Is P a prime?
Yeah, it's a p is a prime. Sorry, I forgot to mention. P is a prime actually. Yeah. Okay. So this is a technical definition of splitter, but I'll explain it using simple words again. So what we have here, first of all, what does this splitter represent? In can someone mute because it's echoing? Yeah. Yeah. So what does splitter represent? So it is actually a family of functions actually. So we'll go line by line in detail. So it's a family of functions from set 1 to n to set 1 to l. So that was the shorthand representation. So it is a family of functions, but it has some special properties actually. So if you take any set S which is a subset of n and is of size k, then there will exist a function f in this family of functions such that it sort of distributes evenly. By that, what I mean is that basically what you're doing using this function, you are numbering each element of S by some number 1 to n. Okay. So you count for each number how many number of elements in S is attached. Like, okay, let me take help of one. Yeah, I'll use this to explain actually. It will be better because the technical definition is quite detailed. Okay, so you have some. So you, like just consider this as S, just for the representation sake. It is a subset of 1 to n. So what we are doing using the function f, we are assigning a number to each element. Okay, here. So we are assigning a number. So suppose we assigned a number 3. We assigned a number 4. We assigned a number 2. And say we assigned a number, say, 1. Okay. So I have assigned the number in this fashion. Okay. So by f inverse of a number 1 and then doing mod here. By this, what I mean is I want to count the number of elements which have been assigned 1 using this function f. Okay. So number of such elements in this example, f inverse of 1 is 1 actually. Same f inverse of 3 is 1, f inverse of 4 is 1, f inverse of 2 is 1. If F inverse of phi mod will be 0 actually, because there is no element which has been assigned 5. This is S actually. Yeah. So this is what I mean by F inverse actually. So it's basic standard definition. So what it means is that for every set S, which is of size K, if you take any element from this set 1 to L and you take its inverse and you see in S how many number of elements got that number actually, and you compare it with any other number, like this is one representation, F inverse of J1 intersection S, which basically means that number of elements in S which was assigned the value J1 using this function F. And similarly you do for J2. So the difference between this mod will be at most 1 actually. So let me explain it again here. So what it means is that take 1, 2, 3, 4, 5. Okay. And you do this F inverse thing, intersection S. Okay. If we just focusing on that S, so you'll see the value is 1, 1, I mean mod value obviously. 1, 1, 1, 1, 0. So what this property wants is that a difference between any two numbers will be at most 1. If you calculate this F inverse intersection S. So this will be 0. So it will be at most 1, the difference. So, sorry. So if we had some different function, and if we were doing intersection, like different function in the sense that some different type of coloring, not say functions, and it had 2, 2, 2, 2, like the F inverse values and 1. So the F inverse value should be of this type actually. It can't be arbitrarily different. Like it can't be 3, 0, 1. Like it can't be this one, because see 3 minus 0 is 3. So we want that the difference between any two numbers should be 1. So this is the kind of definition we are looking at. So this is quite important. So if anyone like if it can be confusing, so if there is any doubt, please ask me. I can explain again. Hello? Hello, am I audible?
Yes, you are audible.
Yeah, so was it clear till now, this definition?
So, yeah, to me, yeah.
Yeah, so if but yeah, you just for 1 minute you can read this definition in case I'll just you can read it. The definition is quite simple. So I'll just read it again in case someone didn't get it. So basically it is a family of functions from this set 1 to n to set 1 to L, such that for every subset S which is of size K, we have a function. Okay, such that this F inverse values will differ only by 1 among themselves. So difference between any two F inverse values will be only 1, at most 1. It can be 0 also. It can be 1. Okay. So this was the definition of splitters. So so in more detail, so like you can consider it to be in this form, as I was telling it there. So you can consider that you have n objects, okay, and you're coloring with L colors actually. Okay, so you're coloring the objects with L colors, and mainly we use splitters in the case where this K is less than L actually here. This K is less than L, we use in that case. If so in that case it's very easy. So it's very easy to explain also splitter. that if we take any such set S, then there will exist a function f such that it will color each element of that set differently. That's what we want basically. So in simple terms, this if L is greater than K, and if you consider these functions as some coloring, like like this is a set of objects 1 to n, and you are coloring using L colors. So color 1, color 2, color 3 up to so on. So what this splitter tries to do is that if you take any set of objects such that the size is K, then there will exist a function f which will color each element of this set S differently. So this is what we are looking for. So this is kind of a nice family of functions actually, which will be quite useful, which I'll show how. But this is the general aim which we want. So, okay, so before looking at some like very nice constructions, like what can be some very naive way of creating such functions, like family of functions. So can someone tell, like it's a very naive way of creating such functions such that this property holds actually, this property here. So can someone tell, like it's very easy actually. Very naive way of creating such family actually. Anyone would like to try? Like it's very easy actually. Like it's very easy. So like what one easy construction can be like just
All functions or something?
Yeah, all functions is yeah, all possible functions is one direct naive way. Yeah. So in that we'll always have one function which will satisfy this property because all functions are there. That is one very naive way. So the size of that function will be k to the power n, roughly, I guess. K or like L to the power n, I guess. Yeah, if you are using L colors, then it will be L to the power n. But we can do it n to the power L also. Yeah.
Can we do like for every subset of size k, we introduce one function?
Yeah. That's what I was looking for. So that is one naive way. So the complexity will be n to the power k, like the time to create that family and the size of that family. Yeah. So that was the naive method which I was looking for. So it will be n to the power k. So take any subset of size k and you introduce one function for it. Yeah. So so the next question is, can we do anything better than this? Oh, sorry. Yeah. So can we do anything better than this? Yeah. So we can we can do better than that actually. So I'll look at one splitter which is of this form, n, k and k square log n. I'll explain the construction of this, which is very simple and very interesting. And using similar ideas, we can create other splitters also. So let me explain you this thing. So like we want to construct a splitter n k square log n. So basically we have n objects. We have k square into log n number of colors, and so the property should be on any subset of size k. Like any subset of size k should have different color for at least one of the functions in this splitter actually. So that's what we want. So that's why I call n k square log n splitter. Okay. So we prove this lemma, which is very easy. So take a subset of size k. Okay. Then okay, so there's a typo here. This comma should not be there. So there exists a prime p less than k square log n such that this function here, x2 x mod p, okay, is 1 to 1 on S. So 1 to 1 is nothing but each element of S gets a different color. It's same thing. So in mathematically, whenever x is not equal to y, x mod b should not be equal to y mod b. So so what we are going to show is that for any set S, there will exist a prime p such that this function is 1-to-1 on S actually. So it colors each element of S differently. Yeah. So we will show it now. Okay. So consider a set like x1, x2 up to xk. S. So this is an arbitrarily chosen set, and let T be the product of xi minus xj. Okay. I less than j. Okay. So basically product of all pairs. Okay. So log mod t is at most k choose to log n. So this happens because the difference between any two numbers is at most n, because this is a subset of 1 to n. So any number's maximum value can be n, and any number's minimum value can be is 1. So the difference can be at most n, and the number of pairs is k choose 2. So log mod t is less than equal to k choose 2 times log n, because we do log and it becomes addition. Okay. So this is the thing. Okay. Now suppose it is the yeah.
In the definition of T, is it like product of mod of xi minus xj?
No, it's just xi minus xj. Just xi minus xj. But yeah, we can do mod also, but it doesn't make any difference actually as such. Because I did before doing log, I did mod.
Okay.
Yeah, here. Yeah. So yeah. So suppose assume that every prime p which was less than log k square times log n, it divides this t. Yeah, it divides this t. Assume that this is a typo. This bracket should not be there. Then product of there's some typing error actually. Just one second. This thing should not be there actually. Like just ignore this part. So what I wanted to say was product of all primes such that k square such that it is less than k square log n. It is less than or equal to t, because if any prime is dividing t, then it should be a factor of that number t. So obviously product of all primes which is less than k square log n will be like it will be less than t. That's a basic arithmetic property. Okay, just ignore this thing, like I'll rectify it in, later. So yeah, so this thing happens if every prime p divides t actually. We have a prime number theorem which says that logarithm of product of all primes p which are less than x is x plus small o of x. So this is the prime number theorem. So by this we get that logarithm of product of all primes p such that p is less than this k square log n, it is greater than or equal to k square log n actually. So this is by prime number theorem. So it means that there is a prime p which is less than k square log n which cannot divide t. Because if every prime number was dividing t, then it should be the product should be less than or equal to t. But here we showed that the logarithm of a product is greater than or equal to k square log n, and logarithm of mod t is this should be mod t. Sorry, this should be mod t, not t. So logarithm of mod t is at most k choose to log n. So this product is clearly greater than this. So it means that there is one prime p which does not divide t actually. Okay. So if there is a prime p which does not divide t, so what does it mean? It does not divide this difference basically. And if it does not divide this difference, then x mod p is not equal to y mod v. That's the definition of mod. So it means this lemma holds true. Like for every if we take any set S, there will exist a prime P such that this function is 1-to-1 on S. So this is a very nice proof. So this nicely uses number theory. And now what is our splitter? This is our splitter, like Fp such that P is a prime less than k square log n. Because if as we showed in that lemma, for any set, if we take any set S which is of size k, we'll have a prime P such that the function Fp will color each element of that set S differently. Okay. So this is a property which we wanted. That's why, since it satisfies this property, it is a k square log n splitter. Okay. And what is the number of primes which is less than x? It is approximately x by log k. So if you substitute k by this k square log n, then the size of the family is polynomial. Okay. And previously where we were looking at exponential, not only in k, but like n to the power k. So it's a huge drastic difference actually. Okay. And obviously you can see it can be constructed in polynomial time. Like just identify which is a prime number, which is less than k, and just create these functions. So this is a very nice construction of this splitter. So I hope everything was clear till now. So if something is not clear, feel free to interrupt me. Yeah. So this I'll not prove, just I'll give the construction. I'll like upload the file if you want. You can have a look at the proof why this one holds true. So if we fix a prime number P such that n is less than P, which is less than 2n, fix such a prime number P. So such a prime number will exist. I forgot the postulate, Bernard's postulate or something. Because of that, such a prime number will exist. Then consider these functions actually. Consider like let us define a function fa in the following way. X is mapped to ax mod p, and then that mod p, then mod k square. We are doing mapping in this way. Then we can show that this family fa such that a belongs to z star p. Z star p was nothing but 1 to p minus 1. Okay. Then it is a k square splitter. Earlier we were looking at k square times log n. Now we are looking at k square. Okay. And since p is between n and 2n, this size of this family is order n, and it can be, so you can easily construct it in polynomial time. So it's a very nice property, k square. It's quite useful. And what you can do, you can use this splitter to create a nkk splitter. Construction I'm not showing because it's little bit like in order to understand the construction, I need to explain a lot of stuff. So for now, I'm just skipping the construction. I can show visually how the construction looks like. But before that, let's look at this lemma. So what this lemma says that we can construct a nkk splitter. By nkk, what I mean is that we are going to color using only k colors. Okay. Using k colors, we are going to color every element in 1 to n, such that if you take a subset S of size k, then there will exist a function in this splitter which will color each element of it uniquely. Okay, so that is what we meant by nkk splitter. So we can construct it in time, some function of k into log n. The size is function of k into log n, and we can construct in time some function of k into n log n. So this one lemma, just I can show you the construction. It's a little bit big. In order to explain that, I need to show some previous work also. Just I can visually you can see how the construction looks like. It's all these all are proved using algebra and number theory. So you get like why these all are important. Like, yeah, it looks something like this actually. Each function in nkk splitter. Let me zoom it a bit. So it looks like this. It's a little bit involved, like not that much involved, but it's not as simple as the previous splitters actually. So it looks of this type. Yeah. Yeah. So this was splitters. So now let us go to the interesting part actually, which is the color coding. Let me share the present. Okay. So let us understand this example using one problem actually. So we have this longest path problem where we are given a graph G and a positive integer K. And our objective is to test whether there exists a simple path on K vertices in the graph G. Yeah. Simple path of K vertices. So that's the important. Like shortest path problem is solvable in polynomial time. This is the decision version of longest path problem and it is NP complete. Yeah. So what is a brute force algorithm? Like, so let us assume that K is equal to 4. So we'll select and like we'll check all combinations of 4 vertices and check whether there is a path between them. Okay. So this doesn't have path. This has a path. So there is a yes instance. Okay. So yeah. So what is color coding? Like how does it help us? So what we want to do is that we want to color that vertices of the graph using some set of colors randomly. Okay. So that if we color this like if the solution, if it exists, is colored in a particular way, then we can quickly find it. So that's the entire idea of color coding. So let me explain it using this figure. Suppose it was colored randomly using 4 colors. And we observe that there is a path of 4 vertices where each vertex is colored differently. If we have such a path, then we can find this path very quickly actually. So it can be done using dynamic programming, very easy dynamic programming. So if each vertices of the graph was colored randomly using k colors, then using dynamic programming technique, in time 2 to the power k into n to the power order 1, we can determine whether there exists a path of k vertices such that all the vertices on it have a different color. Like such a path, we call it as colorful path. Colorful path is a path on which is a path where all the vertices have a different color. So this problem we can solve it in time 2 to the power k into n to the power order 1. Like I'll just give a hint. You can try it later on. The subproblem can be that you have a set of colors S and you have a vertex U and you want to determine whether there exists a colorful path such that it uses the colors from S, like all the colors from S, and its endpoint is U. So you can use this as a subproblem and develop your recursive formula and solve this problem in time 2 to the power k into n to the power order 1. 2 to the power k is coming because the number of sets S can be 2 to the power k. So that's why those number of subproblems will be there. So we can solve it quickly. So this is the idea of dynamic programming. But what is the problem? The problem is with random coloring actually, because if we want to solve the original problem of longest path problem, we should be able to color in such a way that all the vertices of this path will be colored differently. But if we color randomly, it might happen that even though such a path exists, here you can see this path exists if k is equal to 4. But it was colored in such a way that it will falsely tell me that such a path does not exist. So what we do something called de-randomizing. So instead of picking a random color, we construct a family of functions f such that one of the functions will guarantee that all the vertices of this solution is colored differently. So that's what we want. So can someone tell which splitter should I use to de-randomize the longest path problem from the audience? We looked at splitters right till now. So which splitter should we use to de-randomize this problem?
Be NKK.
Yeah. We should be using NKK because NKK ensures that if we are coloring using K colors, then there will exist a function in that which will color these K vertices uniquely. Like each vertices will have a different color. And we saw that the NKK splitter can be constructed in this time. So it means that we can solve the problem in time some function of k into polynomial of n. So we are not going to end up with the brute force algorithm, the brute force time complexity, which was order n to the power k, which I showed initially here, brute force algorithm, but we are going to get a better algorithm than that. So this is a like sort of nice application, and it's used in lot of places. And especially if the number of colors is log n, then you will be finding polynomial number of colors. And a lot of problems have this scenario where you have to color using log n number of colors, and you will get polynomial time solution. Whereas if you were just going to use brute force, then it would have been quasi polynomial, means n to the power log n. So you would have ended up with this type of solution, but now you are now ending up with a polynomial time solution. So order n to the power 1. Yeah. So something of this type actually. Yeah. So yeah. So this was a brief like sort of introduction into this thing. Yeah.
Can I use more than k colors?
Like, yeah. You can use more than k colors actually.